This video lecture is going to be on empirical and molecular formulas. So this is just going to expedite this topic as well as streamline it. So it's going to feel like a little bit different from the topics we have been covering with the mole and stoichiometry, but it still uses this particle model to analyze compounds and kind of determine the chemical formulas of them. So as you may or may not have picked up, there are a variety of notations to summarize what makes up a compound. And so there are different ways to describe a compound, and there are empirical, molecular, structural formulas that use chemical symbols and give the subscripts and numerical values to describe what atoms make up and the ratios of the atoms that make up that compound. So there is just the normal chemical formula, and that's going to tell you the composition. You've seen these, sodium chloride, calcium chloride. We've got ethane there, C2H6. That's your molecular formula unit, and it's a ratio there. And then there are other things like empirical formulas, which is the lowest whole number ratio of atoms in a compound. So while the NaCl is 1:1, that's the lowest ratio, the C2H6 could be reduced to CH3 or C1H3 there to emphasize the 1. Now, ionic compounds always show empirical formulas because they're written in a way that shows the lowest whole number ratio of ions that make up that unit. But molecular covalent compounds do not always show that. Okay, so here's just some more examples of empirical formulas. We've got H2O, H3PO4, CH, Fe2O3, iron 3 oxide, and you've got C2H5. Now these ones right here are not empirical formulas because they're not the lowest whole number ratio. This first one could be reduced down to H1O1, and the C6H12O6 could be reduced to CH2O, and the N2O4 could be reduced to N1O2 or just NO2. So an empirical formula is the lowest whole number ratio of atoms in the compound, which you're going to see why you would need that in relationship to the actual formula. So the chemical formula, we also learned how to draw molecules, and we really learned how to do these structural formulas for covalent compounds, okay? So an empirical formula, like a molecular formula, they lack any kind of structural information of how the atoms are positioning themselves or bonding, which is why we did a unit on the notation for how to draw molecules and represent them in a three-dimensional space with Lewis structures, and then the three-dimensional drawings. We've looked at space filling models. Those types are structural formulas, and they can describe a number of different structures, which are known as sometimes isomers, and how everything is connected can greatly determine the physical properties of that. But how do you determine a structural versus an empirical formula and whatnot? That's kind of what we're going to learn. So as an example here, we've got butane, which is C4H10, and butane and isobutane, these two structures here, both contain 4 carbons and 10 hydrogens. Now, their empirical formula, the lowest whole number ratio of those is C2H5, meaning if you did the molar mass of both of those and got the percent composition of C2H5 or C4H10 or any multiple of C2H5, the carbon and hydrogen ratio would be the same. And so that's a difference between like an empirical formula and then the molecular formula is then if something is some multiple of an empirical formula, the lowest whole number, its molecular formula would have a different mass than the lowest whole number ratio, but the percent composition would be the same for C2H5 or any multiple thereof. To just emphasize the difference between a structural versus empirical formula, the structural representation for butane would, rather than writing as C4H10, would be like CH3, CH2, CH2, CH3s. It's connected as CH3, CH2, CH2, CH3. And it actually behaves differently, has different physical properties, melting point, boiling point, density, stuff like that, than isobutane here, or methyl, 2-methyl propane here. And so for this, it's still C4H10, and but it could be written as CH3 with 3 of them, and then CH to kind of represent the structural difference between the two. Okay, so difference between structural versus empirical formula. We've basically, I'm just getting at all of this to show you there's lots of different ways to represent compounds, and there are different places for different ones. How do they determine an empirical formula? So empirical formulas can be determined using mass composition data. So this idea of percent composition. And they can also do it, meaning they can put a sample in something that can analyze what makes up a compound, and it'll tell you the percentages of the ratio of the elements that are present by mass. And they can do that with a chemical reaction. Sometimes they can just analyze it. Sometimes they do it with a combustion analysis, and with something that contains carbon, hydrogen, nitrogen as an analyzer. And it can be used to find mass fractions for carbon, hydrogen, oxygen, and other atoms of a sample for organic compounds. So remember, organic chemistry is just a term that typically means carbon-based chemistry here. Once the relative mass contributions of an element are known, that information can be converted into moles, and we can do mole ratios. And so the empirical formula is going to be the lowest possible whole number ratio of those elements. Now, this is in words what we're going to do, and I'm going to show you what it means. But basically, once you analyze a sample and you say, oh, it's this percent carbon, this percent hydrogen, this percent oxygen, you can use those percentages to get to moles. I'll show you that. And then you have like a relative molar ratio here, and maybe it's like 1 to 2 to 1 there, or maybe it's 1 to 4 to 2. Whatever it is, we can come up with a chemical formula for it, and know the composition, at least an empirical formula. So if you want like a quick little mnemonic device of how to calculate empirical formula, it's always going to be percent to mass, mass to mole, divide by small, multiply till whole. And we can use that. That's real quick if you want it a little bit more written out. If you're given percents of each element, you need to convert them into grams of each element. It's usually easiest to assume you have 100 grams of the sample, because then you can just take the percentages and turn them directly into grams, unless it gives you an amount, and then you have to use that. Whenever you have your amount of grams, you're going to convert to moles, and using the molar mass of, in this case, individual atoms. This is a difference you're going to see in this process, because it is analyzing individual atoms. Even if something would normally be a diatomic, we're going to analyze it as individual atoms. And then you're going to divide by the smallest number of moles once you have them all in moles to get a whole number ratio. And if it's not whole number, then I'll show you what to do. So as an example problem, simplistic one. So a compound is found to have a percent composition of 47% phosphorus and 56.3% oxygen. And we're going to find the empirical formula of this. So we've got 43.7% phosphorus. We're going to assume we have 100 grams of this compound. You can pick any amount, and then you're going to take 43.7% of it, 56.3. But if I have 100 grams, then I have 43.7 grams of phosphorus, and I have 56.3% oxygen. So I have 56.3 grams of oxygen, and it's the atom oxygen. This is not elemental oxygen. It's oxygen within a compound. So percent to mass, and then we're going to go mass to mole. So We're going to take the molar mass of phosphorus off the periodic table. It's 30.97, and get to grams of it. So the 43.7 divided by the molar mass, and we have 1.41 moles of phosphorus in this compound. And then for the oxygen, okay, here it is grams of just oxygen atoms. So it's going to be the 16.00 is in 1 mole of oxygen atoms, because it's how many oxygen atoms are in this compound. So we're going to take the 56.3 and divide it by the molar mass, and we have 3.52 moles of oxygen. So the relative ratio of moles in this compound is this. Now, you're going to divide by the smallest number of moles that you had. So I'm going to divide both by 1.41 to get whole numbers here. So we have relatively 1 phosphorus to every 2.49, 2.5, okay? 1 phosphorus to 2.49 oxygens, which this is, 2.5. So it would be written as P1O 2.5. That's the lowest ratio here, but then you multiply until you have all whole numbers. So we can't have half of an oxygen atom in a compound. So we're going to multiply it by 2. So the empirical formula here would be P2O5. So this compound, its empirical formula, the lowest whole number ratio of atoms in this compound based on that percent composition is P2O5. Okay, so this is the empirical formula, and this is how they determine oftentimes what, like how to prove that something is like water or not water. They can do the percent composition of the liquid and see what's in it. If it's just hydrogen, oxygen, the percent composition of oxygen and hydrogen would be different in water, which has the formula H2O, versus hydrogen peroxide, which would be H2O2. You'd have a different percent composition and molar ratio of those atoms in a compound. Let's see here. I'm gonna do this one real quick. If you want to pause the video, and then when you unpause it here, it's gonna just have the answer for this one, so you can kind of check your work and see if you're getting how to solve for empirical formula here. Here I have the problem solved. You should have gotten C10H7O2. You can look back at this and see how you did on that. So how do you then go from an empirical formula, so like, to a molecular formula, the actual number of atoms in a compound, because they can be different for covalent compounds. Ionic compounds will always show the empirical formula be the same as the molecular formula. And so here I have formaldehyde, or we learned it as methanol. Acetic acid or ethanoic acid is the proper IUPAC name, and glucose. Here, they all have an empirical formula of CH2O, meaning they have the same percent carbon to hydrogen to oxygen, but the molecular formula of formaldehyde is CH2O, but ethanoic acid is C2H4, it's 2 times that, and glucose is 6 times the empirical formula. So a molecular formula for covalent compounds shows the it's based on the actual number of atoms in the compound, and it can be the same as you see for formaldehyde. It can, and for all ionic compounds, the empirical and molecular formula would be the same. But for covalent compounds, it could be a multiple of that. And so, how do you get that? If a compound was C3H8, its molecular formula could be C3H8. It could be C6H18, C9H24, etc. And it's always a whole number factor by this. So to get to the molecular formula from the empirical formula, things that you need to know. I mean, basically, it's just a proportion of the molecular formula molar mass, so mm molar mass. You have to basically solve for that or be given it. to the empirical formula molar mass, you're going to get some number. It's either 1 or more than 1, and then you multiply by the empirical formula to then get the molecular formula. So you either have to be given or have to be able to solve for the molar mass of the unknown molecular formula. So you have to give that information. They'd have to analyze that to give it to you. Then you also either have to be given the empirical formula or you have to solve for it like we just did. And then you divide the molecular formula by the empirical formula, and whatever the multiplier is, you adjust the empirical formula. So as a simplistic example, it wants to know what is the molecular formula. If the molar mass, so of the whole compound, is 60.12, and its empirical formula is CH4N. So it's molecular formula molar mass by empirical formula molar mass. You're going to get some number. And then we multiply by that by the empirical formula. So it tells us the molecular formula molar mass is 60.12 grams per mole. We have the empirical formula, so we're just going to add up the molar mass of that, 12.01 plus the 4 carbons, 4.04 plus nitrogen, 14.01, and we're going to get 30.06 grams per mole. You're going to get 2 as your number. So the molecular formula, the actual number of atoms in this compound, is 2 times the empirical formula of CH4N. So the molecular formula is C2H8N2. And that would be the actual number of atoms that would be in that compound. It can also be something like this where you have to go through the whole process. So I'm going to, again, you're going to attempt to solve this. When you're ready to check if you did it correctly, then just unpause the video and I will have the work shown for it. So far, I have solved for the empirical formula, which is the C4H5ON2. The molar mass of that compound is 97.11. He wants to know the molecular formula. Molecular formula is the molecular formula molar mass over the empirical formula molar mass. You get some number. If we do that, it gives us the molecular formula molar mass is 194.19 grams per mole. If we put that over the 97.11 grams per mole, we're going to get 2, really close, 1.999, so 2. And so the molecular formula is going to be 2 times the empirical formula, so we're going to get C8H10O2N4, and that's all of the atoms in this compound. Okay. The last kind is using the type of problem for these is with a chemical reaction, and this one's going to have a little bit more involved with it. So here we have a problem. It has ethylene glycol. It's used as an automobile antifreeze and into manufacturing. And it's just gives you some other information. It says combustion of 6.38 milligrams of this compound gives 9.06 milligrams of carbon dioxide, 5.58 milligrams of water, and the compound only contains carbon, hydrogen, oxygen. So it wants to know what are the mass percentages of the elements in the compound, what's the empirical formula, and then we'll get to the molecular formula as well. So combustion is combustion of a hydrocarbon, and it says it contains carbon, hydrogen, and oxygen. We don't know the ratios. That's being burned in the air. When you burn a hydrocarbon in the air, you're going to make carbon dioxide gas and water vapor. And it tells us that we combusted 6.38 milligrams of this, and we formed 5.58 milligrams of the water. Yep, let me move that over to the water. And 9.06 milligrams of the carbon dioxide. So here you're like, well, how do I do this? I haven't been given percentages and whatnot. Well, all of this, you have 9.06 milligrams of carbon dioxide, but all of the carbon that's in the carbon dioxide came from the amount that was in this compound. So we can do we can figure out the percent of carbon in CO2 and then take that percent out of the 9.06 milligrams. Same thing with all of the hydrogen that came out of the reaction came from, was put into the water. And then after we have those two, we can subtract from our total to get how much oxygen was in the compound. So with that, the molar mass of carbon dioxide is 44.01. There's one carbon here, so 12.01 grams of carbon would be in 44.01 grams of CO2 times 100 is going to give us the percent carbon in CO2 there. So if we do that, we're going to get, it's 27.3% carbon in CO2. So if we take 0.273 times the 9.06 milligrams, then we can get how many of those milligrams are in that. So there are 2.47 milligrams of carbon that combusted, okay? For the hydrogen here, the molar mass of water is 18.01, or sorry, 02 grams water, and there'd be 2.02 grams of hydrogen in the water. So we can get the percent hydrogen there, and that is going to be 11.2%. And if we take the decimal abundance times the 5.58 milligrams, we're going to get 0.626 milligrams of hydrogen is what combusted. So from the 6.38 milligrams, if we subtract 2.47 milligrams, which is carbon, and minus the 0.626 milligrams of hydrogen, we can get how many milligrams of oxygen are left over. And we get, your calculator say 3.284 milligrams of oxygen. With sig fig, since all of these go, you have two that go to 2 past the decimal, we can just say 3.28 milligrams of oxygen. So here we don't have the percent compositions, but we have the mass amounts of each of these. So then we can use those mass amounts of each atom to get to moles and solve for it that way here. So next we're going to solve for the empirical formula. I could have also just changed all these amounts to grams, and I left them as milligrams, but I'm going to assume now, I'm going to scale them all up by 1,000 and say I have 2.47 grams of carbon relative to 0.626 grams of hydrogen to 3.28 grams of oxygen. And then from there, I'm going to get to moles. So how many relative particles would I have of each? Doing the molar masses here of the atoms. And we get 0.206 moles of carbon, 0.61620 moles of hydrogen, 0.205 moles of oxygen. And then we're going to divide by 0.205 by each one, the smallest mole amount. you're going to get 1 carbon, 1 oxygen, and 3 hydrogens here. So the empirical formula is CH3O. That's the empirical formula from this compound. Now, it then says if the molecular molar mass is 91 plus or minus 2 grams per mole, then what is the molecular formula of the compound? So it's not giving us the exact one, but if we find the molar mass of this empirical formula, which is going to be 12.01 plus 3.03 for the 3 hydrogens plus 16, we get 31.04 grams per mole. This is the molar mass of the empirical formula. You can see if you take, it's 91 plus or minus 2 grams per mole. Sometimes they give you like a range. We take that divided by the 31.04 grams per mole. You're going to get on your calculator, it's like 2.93. You might be like, is that close enough to anything? Yeah, we can say it's about 3 times. This is plus or minus 2 grams per mole. So if we increase it, then it's going to be closer to 3. So the molecular formula is going to be 3 times the empirical formula of CH3O. And so you're going to get C3H9O3 as the molecular formula there. So, you know, how did they analyze compounds and everything? Well, this is how they do it. And so hope this video lecture helps you understand this. You've got some practice problems to help.